chapter is amines. First part is nomenclature. The nomenclature is very easy. Just replace the E of alkane by amine. It becomes alkanamine. And this is the IUPAC nomenclature of amines. For example, here CH3 group is attached to the nitrogen, and this can be named as methanamine because the alkane is methyl group, so it will be methanamine. According to common name, it is written as methylamine. Similarly, this is written as dimethylamine according to common name, and it is written as N-methyl methanamine according to IUPAC name. Then it is trimethylamine according to common name, and N,N-dimethylamine according to IUPAC. So just name one carbon as methanamine, for example, and the other two as N,N-dimethyl, right? Let us see some more examples. For aromatic compounds, this is named as N-methylbenzamine because this CH3 group is attached to nitrogen and one phenyl group is also attached to this. So it will be N-methylbenzamine. Here two ethyl groups attached to nitrogen, so it will be N,N-diethylbenzamine. Here it will be 2-methylbenzamine. N-phenylbenzamine. Phenylmethanamine. It's written as methanamine because CH2 group is attached to the nitrogen, and further this benzene ring is attached to the carbon. So it will be phenyl. This is not a benzene, it is phenyl group. So phenylmethanamine. To name the salts of amines, we will replace amine by ammonium and replace aniline by anilinium. This is the case of salts, that is quaternary ammonium salts. Here R3N positive X negative is written as trialkyl ammonium halide. It is written as anilinium halide, right? Next is the classification. There are 4 types of amines: primary, secondary, tertiary, and quaternary. Primary is RNH2 group, that means one alkyl group is attached to the nitrogen. In secondary, 2 alkyl groups are attached to the nitrogen. In tertiary, 3 alkyl groups, and in quaternary, 4 alkyl groups are attached, and nitrogen gains a positive charge because it is bonding beyond its valency, right? Then we have structure. The structure of amines are similar to ammonia, right? It have a tetrahedral geometry and a pyramidal shape. The difference between shape and geometry is that in case of shape, we don't count the lone pair of electrons. Only the bond pairs are counted, which are forming a pyramidal shape. In case of geometry, lone pair is also counted, which is forming a tetrahedral geometry. And the hybridization of nitrogen, the central metal atom, is sp3, similar to ammonia. Then we have the preparation of amines. The first method is by reduction of nitro compounds. When nitro compounds are reduced in presence of some reducing agents, it forms aniline, that means amines, plus water. The reducing agents that can be used in this reaction are hydrogen in the presence of nickel, platinum, palladium, hydrogen in the presence of Rene nickel, iron plus HCl, which forms FeCl2 plus hydrogen. This hydrogen acts as a reducing agent. Tin plus HCl, tin chloride plus HCl, which again produces hydrogen, which is a reducing agent. These all can reduce aliphatic plus aromatic nitro compounds, but the only reducing agent, that is lithium aluminium hydride in the presence of ether, this can only reduce aliphatic nitro compounds. The second method of preparation of amines is reduction of nitriles. When nitriles are reduced, they form amines. The reducing agents that can be used are lithium aluminium hydride in presence of ether, hydrogen in presence of nickel, platinum, palladium, sodium in the presence of alcohol, and this reducing agent is named as Mendius reduction. The reaction is named as Mendius reduction when this reducing agent is used. For stepping up the series, that means to add more carbons to the compound, we use this method. Alkyl halide, in the presence of alkyl halide we add sodium cyanide, NaCN, it forms RCN because NaX is replaced, and we form RCN in the presence of hydrogen. That means we reduce RCN to form RCH2 NH2. This is an amine with one carbon extra. This is the stepping up of series. The next reaction is Gabriel phthalimide synthesis, and this is a very important reaction for the preparation of amines. In this reaction, we can prepare primary amines, right? In this reaction, we use phthalimide. Firstly, let's see how phthalimide is prepared. Phthalic acid is taken and it is heated. From here, it loses water, OH and H, right? And this oxygen combines with the carbon in this way. Now we add ammonia, NH3. From here again, water is lost when it is heated and we get phthalimide. So simple. Now this phthalimide is treated with KOH. From here again, water is lost in the presence of heat when it is heated, and we get potassium phthalimide. This is potassium phthalimide because the hydrogen is replaced by potassium group, so it is named as potassium phthalimide. Now this potassium phthalimide is reacted with RX, alkyl halide. From here KX is removed and we get N-alkyl phthalimide, right? N-alkyl, because alkyl group is attached to nitrogen. Now here we attack the carbon and nitrogen with water. The OH is partially negative group of water and hydrogen is positive. Similarly, nitrogen is a negative group and carbon will be positive. So this negative OH will attack on positive carbon and hydrogen positive will attack on nitrogen. And this step also takes place from this side. So from here OH is attaching, so OH is attached to both the carbons, and the hydrogen is attacking on the nitrogen, so RNH from above side and one more H from the lower side, so it will form RNH2. That means amine. This is the primary amine and this is phthalic acid, right? So we can see that phthalic acid is produced at the end of reaction, which we initially used to prepare phthalimide. So it is a benefit of this reaction. This reaction also has some limitations. Aromatic primary amines cannot be prepared by this method, aromatic, right? Because aryl halides do not undergo nucleophilic substitution reaction very easily. This means that this halide group does not break from this benzene ring very easily. This do not leave easily due to partial double bond character in this. Also 2 degree and 3 degree, that is secondary and tertiary amines, cannot be prepared by this method because they prefer elimination more than substitution. The next method of preparation of amines is reductive amination of aldehydes and ketones. This is not animation, be clear, it's amination, right? So in the presence of aldehyde, we add ammonia to aldehyde. From here water is removed when we heat the mixture and we get aldemide. This is aldemine, right? Aldemine is from in place of oxygen, nitrogen and hydrogen is attached, that is NH group is attached. Then we reduce this by adding some reducing agent, we get 1 degree amine, that is primary amine. This is R group, carbon and NH2 group, right? Also when we do the same with ketone, water is removed, ketamine is formed, right? And on reduction of ketamine, 1 degree amine is formed. It is called amination because the step 1, that is from here to the formation of aldemine and ketamine, it is called amination, addition of ammonia, and here it is called reduction, right? So it is called amination overall. The reducing agents that can be used in this reaction are hydrogen in presence of nickel, platinum, palladium, and NaBH3Cn. It is known as sodium cyanoborohydride. Sodium cyanoborohydride, right? The next reaction is Hoffman-bromamide degradation. In this method, 1-degree amides, either aliphatic or aromatic, are treated with bromine and alcoholic KOH to produce primary amines with one carbon less than the parent amide, which is called stepping down the series. And this method is a very important method. We take 1-degree amide, either aliphatic or aromatic. From here, CO is removed and we get RNH2, that is 1-degree amine, in the presence of bromine and alcoholic KOH. And also we get KBr plus water plus K2CO3. The mechanism of this is usually asked in exams, so it's also important. Let us look at the mechanism of this reaction. When bromine and KOH react, bromine and KOH are the reactants. They react to form KBr plus KOBr plus water. The KOBr formed here, it is a very strong base. It reacts with the amide, the primary amide which we used in the reactants, and take away the OH negative group from here. We are taking KOBr as OBr negative, right? We are not writing K positive. OH negative is removed and we are left with R, C double bond O as it is, N, H as it is, and Br with nitrogen. Also, nitrogen is having a lone pair of electrons. Now this bond shifts to the nitrogen when OH negative attacks on the hydrogen. So here nitrogen will get a negative charge, and now we remove Br negative from here. This negative charge, including this bromine, this bond is being removed. So nitrogen is left with one more lone pair because one of its bond is free now, right? Now this lone pair will shift to this bond when this alkyl group will attack to this nitrogen. So we get R single bond N, double bond C, double bond O. R bonded with nitrogen, and this becomes double bond because this lone pair is shifted here. C double bond nitrogen. Clear? Now basic hydrolysis is done. We get RNH2, that is the 1-degree amine, plus CO3, and from this CO3 we get K2CO3, right? Next topic is methods of separation of primary, secondary and tertiary amines. We can use fractional distillation or by chromatography techniques, or the third method is chemical methods, right? There are two types of chemical methods, Hoffman's method and Hinsberg's method. Let us see at Hoffman's method first. Hoffman's method, the mixture of amines is treated with diethyl oxalate. When the primary amine forms a substituted oxamide solid, the secondary amine forms dialkyl oxamic acid ester, that is liquid, and tertiary amines do not react. Okay, let us see what this means. Initially we have the mixture of all types of amines, 1-degree, 2-degree and 3-degree. The mixture of amines is treated with C double bond O, COOET, COOET. This is diethyl oxalate, right? ET is C2H5 ethyl group. So when this reacts with the mixture, from the mixture it reacts with 1-degree amines to form substituted oxamide. Here alcohol is being removed, 2 molecules of alcohol, ETOH, C2H5OH is removed, and we get substituted oxamide, which is solid. When this molecule reacts with 2-degree in the mixture, it forms dialkyl oxamic ester, which is a liquid. So plus 1 molecule of ethanol. And when this molecule reacts with the 3-degree amine, no reaction takes place. So because of no hydrogens in the 3-degree amine. So it is clear that one is solid, one is liquid, and the third one is not even reacting with this compound. So we can easily separate 3 of them, right? Now we have separated all of them, but how to recover amines from these dialkyl oxamic ester or substituted oxamide. Let's see. Regeneration of amines. This is the product formed when 1 degree amine reacts with the diethyloxylate. In the presence of KOH, it forms COOK plus 1 degree amine, and hence amine is recovered. Similarly, 2 degree is recovered when this reacts with KOH plus ethanol, and 3 degree was already there with us, right? The second method is Hinsberg's method. Hinsberg reagent, para-toluene sulfonyl chloride, or commonly called tosyl chloride and shortly written TSCl. It is the Hinsberg reagent. When TSCl reacts with 1 degree amine from the mixture, HCl is removed and we get this product. And when this reacts with NaOH, it forms this, which is soluble in NaOH, right? Now, second, when TSCl reacts with 2 degree amine, it forms this, which is insoluble in alkali NaOH, right? So one is soluble, one is insoluble, and the third 3 degree amines are not even reacting with the TSCl, so 3 of them can be easily separated. Now, how to recover the amines? Firstly, from this we add HCl to this, we get this. Now we add water plus HCl in this compound to get this plus RNH2.HCl. This is primary amine hydrochloride. To primary amine hydrochloride, we add NaOH, we get 1 degree amine, NaCl plus water. So here we have recovered 1 degree amine. To recover 2 degree amines, we add water plus HCl to this insoluble solution. Then R2NH.HCl is gained, secondary amine hydrochloride. To this we add NaOH and we get 2 degree amine. And 3 degree was already there with us because it doesn't reacted with the TSCl. The next topic is physical properties. The first is physical state. Amines when 1 to 2 carbons like methanamine etc. are gases at room temperature and smell like ammonia. Amines with 3 or more carbon atoms are liquids at room temperature and have a fishy smell, right? Amines with more than 10 carbon atoms are soft solids and have no odor. Aromatic amines are oily liquids and have unpleasant smell and are generally toxic. In general, all amines are colorless, but on keeping for long time, they show light yellow to brown color. This is due to the oxidation of amines. Amines are oxidized in presence of light to form CO2 plus water and NO2. This NO2 is responsible for the coloration of amines. Second property is melting and boiling points. As compared to parent alkanes, they have high boiling points. This is because in addition to van der Waals forces, they are also associated through intermolecular hydrogen bonding, right? As it is shown in this figure. As compared to alcohols of comparable molecular mass, boiling points of amines are lower because oxygen is more electronegative and nitrogen is less electronegative, so the hydrogen bonding is stronger in case of alcohol and weaker in case of amines, so amines are having less boiling point than alcohols. If we talk about isomeric, primary, secondary and tertiary amines, the order of boiling points will be 1 degree, more than 2 degree, more than 3 degree. This is because in 1 degree the surface area is greater and hence van der Waals forces are more, so boiling point is more. In case of 3 degree the surface area is less, van der Waals force is less and boiling point is less. Stereochemistry of amines. This is structure of amine. The mirror image of amines are non-superimposable and such amines are disymmetric or chiral and should exhibit optical activity and should exist in 2 enantiomer forms because of non-superimposable images, right? But due to the presence of pyramidal shape and lone pair, flipping occurs very fastly between levo and dextro isomers, like umbrella in fast wind. So we get a racemic mixture due to which it is not possible to separate or even detect any form individually. But quaternary ammonium salts exhibit optical activity as they have tetrahedral geometry, so flipping it is not possible in this, right? As you can see from these images. Now, a very interesting topic of this chapter is basic nature of amines. Amines are basic in nature, which can be shown by following reactions. Amine, when reacts with water, it forms RNH3 positive plus OH negative. It takes H positive from water, and hence, according to Arrhenius theory of bases, bases are those which gains H positive, and hence amines are basic in nature. Now, also they have a lone pair to donate, so according to Lewis theory, they are basic in nature. Then again, they can attain H positive. They can get H positive to form RNH3 positive. So they are Bronsted-Lowry bases also. Now, how to express the basic character of amines? This reaction RNH2 in the presence of water gives RNH3 positive plus OH negative. We know Kc is equal to concentration of products upon concentration of reactants. So concentration of products upon reactants is written like this. Now this water goes to this side, right? We are left over with this. Now Kb is, when these both combine, they form Kb. Kb is called the dissociation constant of base. More the Kb, more will be OH negative produced, because Kb is directly proportional to OH negative, and hence more will be the basic character, because we know more the OH negatives produced, more is the basic character. Or we know pKb is equal to minus log of Kb. pKb is the power of dissociation constant of base. So more the pKb, it is the negative of log Kb, so lesser will be the basic character, right? Now let us compare the basic character of the following. First is amines and ammonia, 1 degree, 2 degree, 3 degree amines, aliphatic and aromatic amines, effect of substituents on aromatic amines, aryl amines and alkyl amines. So we're gonna compare these 5 in this video. The first is amines and ammonia. This is ammonia, we can see NH3, and we have amine here. This is our NH2. We know R group is electron releasing group. So it releases electrons to the nitrogen, and hence the electron density on nitrogen increases, and hence it becomes a good donor of electrons. So it is a strong Lewis base, because Lewis bases are those which donate electrons. Second is the comparison of 1 degree, 2 degree and 3 degree amines. It is very important. In gas phase, 3 degree is more than 2 degree is more than 1 degree. This is the basic character. This is R3N, that is trialkyl amine, 3 degree amine. Here 3 alkyl groups are present, 3 electron releasing groups. So the electron density is the maximum on the nitrogen group. In case of 1 degree, only 1 alkyl group is present, so electron density is least. So this is most basic and this is least basic, and it is the intermediate. But in the solution phase, we have 2 cases. For CH3 group, the order is 2 degree more than 1 degree more than 3 degree. But for ethyl and the other groups, it is 2 degree more than 3 degree more than 1 degree. So let us see how it happens, how the order is being given to these 1 degree, 2 degree and 3 degrees. Now explanation. The first effect that affects the order is inductive effect, that is plus I effect. 3 electron releasing groups, more electron density, so best donor. 1 electron releasing group, less density, so it is the weak base, right? So the order is 3 degree more than 2 degree more than 1 degree according to inductive effect. The second factor is steric effect or steric hindrance. Here, nitrogen is attached to 3 alkyl groups, so it is sterically most hindered. Whereas in 1 degree it is only attached to 1 alkyl group, so it is least hindered. Here, due to more steric hindrance, it is difficult to approach the nitrogen atom, so it is a poor donor. So the order must be 1 degree more than 2 degree more than 3 degree. The third effect is solvation effect. 1 degree amine, when reacts with water, that is in aqueous medium, forms RNH3 positive plus OH negative. This is highly solvated, highly stable. More the solvated it is, more it is stable. So more the stable it is, the formation will be more, and the release of OH negative will be more, so basic character will be more. Let us see at the solvation. This is the solvation of this 1 degree amine with water. In case of 2 degree amines, in aqueous medium they form R2NH2 positive plus OH negative. This is the solvation shown here, which is lesser than 1 degree amine because only 2 hydrogens are there and 2 alkyl groups are there, right? Now in 3 degree amine, in aqueous medium they form R3NH positive plus OH negative. Only 1 hydrogen, so solvation is the least solvated, so least basic. So the order is 1 degree more than 2 degree more than 3 degree, because 3 degree is least solvated, so least basic. So from the 3 effects that we have studied now, the conclusion is, though all the 3 factors play an important role in deciding the basic character of amines, but inductive effect plays the most prominent role. According to plus I effect, we have seen that 3 degree more than 2 degree more than 1 degree. As you can see here, we have already done. But the remaining 2 factors, that is steric and solvation, do not favor it at all, due to which the basic character of 3 degree amines decreases. The steric and solvation factors favor primary, that is 1 degree amines, but the most important factor, that is inductive effect, favors the 3 degree, that is it favors 1 degree the least, so making it least basic. 2 degree amines are most basic because they have a high inductive effect and solvation effect, and steric hindrance is also less. Hence we can say the order is in this way. Comparison between aliphatic and aromatic. We can see aromatic, the lone pair shifts to this point and this one shifts here, so resonance takes place, due to which the lone pair becomes delocalized. It spreads over the ring, benzene ring, so the availability will be less of lone pair, so basic character will be less. But in case of aliphatic, the basic character is more because lone pair is localized, easily available. Aralkyl and aryl amines. In case of aralkyl amines, this lone pair is localized. Due to localization, its availability is more and hence strong Lewis base. In case of alkyl amines, the lone pair is spread over the ring, so it is delocalized, and hence alkyls are weaker bases than aralkyls. Fifth is effect of substituents. When substituents are attached to nitrogen atom, they are directly attached to nitrogen. Okay, when no releasing group is there, the basicity is least. When one releasing group, it is more, and when there are 2 releasing groups, the electron density on nitrogen increases and hence basicity increases. This is 1 degree amine, 2 degree amine and 3 degree amine. When substituents are attached to the ring, okay, 2 cases, if it is electron releasing group and if it is electron withdrawing group. In case of electron releasing group, the group increases the electron density of the nitrogen and hence basic character increases. But electron withdrawing group on the other hand, it withdraws electrons and hence it decreases the electron density on nitrogen, so basic character decreases. Hence releasing groups increases the basic character, and withdrawing groups decreases the basic character. Then we have ortho effect and para effect. Every ortho-substituted aniline is less in basic character than parent and other substituted anilines. May the group be electron releasing or may it be electron withdrawing. That means ortho group is always least basic than parent as well as substituted anilines. Either the group is releasing or the group is withdrawing, ortho group is always least basic. This is ortho effect. Para effect is the base strengthening effect of electron releasing group, base strengthening effect. And similarly, base weakening effect of electron withdrawing groups will be more prominent, more pronounced at para position than meta position. So para position will experience more basic character. Either it is if it is electron releasing group, it will be more basic para group, or if the group is electron releasing group, so para position will be more acidic. That means lesser basic. So the effect is more pronounced at para position of electron releasing and electron withdrawing groups than the meta position. The last topic of the chapter is amine salts as phase transfer catalyst. Tetra-alkyl ammonium ions R4N positive. They are obtained from tetra-alkyl ammonium salts, that is R4N positive X negative. They have an unusual property. What the property is? They are soluble in aqueous medium due to their ionic nature, as we can see. Also, at the same time, they are soluble in non-polar organic solvents due to presence of 4 alkyl groups, right, attached to the nitrogen. These ions are able to move back and forth between two phases. That is, they can move between aqueous and organic phases back and forth, right? Let us see this reaction. Rx can dissolve in organic solvents. NaCN can dissolve in aqueous medium. So, from here NaX is removed, we get RCN. But for the reaction of both of these, they cannot react with each other because they have to come in contact with each other to react with each other. But this is not possible because Rx cannot dissolve in aqueous medium and NaCN cannot dissolve in organic medium. So to do so, to mix them, to react them, we need something like R4N positive X negative tetra-alkyl ammonium salt so that they can react with each other. Hence, because they can go both in organic as well as inorganic medium, so they are called phase transfer catalyst, as they travel in two phases, and they behave as a catalyst as well, so they are called phase transfer catalyst, right? The examples are C8H17Br or this, right? Now let us see. Here RCN is reacting with this phase transfer catalyst to form NaCN. Again, this is aqueous medium and this is organic medium. They cannot dissolve in each other, but for the reaction we use this phase transfer catalyst. Now in the same medium the reaction can occur easily. So X is replaced by Cn and Cn is replaced by X. Again, for change of phases, this is required. This converts NaX to Rx because this is the phase transfer catalyst. And again, for the same medium, this can easily convert to RCN and Cn can be replaced by X here. So that was all about the chapter. Thank you.